similar to the resistance case. Whereas the other kind of capacitance is MOSFETs, voltage capacitance. So some of them are voltage dependent, some of them are voltage independent. Again, same principle. Voltage independent capacitance, mostly because the distance between the two plates are more solid. So it doesn't matter which voltage applied, you always have the same distance. So this is the independence. But what the difference of this capacitance different from what we learned in other courses is this. We consider the second component of capacitance, which doesn't matter which case. One is area, and the other is the fringe. So all this very brief to summarize what we had in previous weeks. So we studied RC because these are elements really affect the performance, and mostly the performance of the speed or delay, in other words, and the power dissipation. And we talked about static power dissipation in previous beginning lectures. And of course, we are going to talk about more major components in this power dissipation dynamic now. So I hope today we have time to cover. One is time delay, how RC is affected. The other is the power dissipation. And about the delay estimation. This is very essential in all the circuits. And in analog circuits, we talk about is not a delay estimation. Such terminology is called the frequency response, bandwidth. So this is related to delay, because when you have an excitation, how fast the response will be. So this is, they called the passive. But in digital is just as I sketched in this diagram. If you have such input and very simple inverted circuit, you have such output inverted, logic is 0 and 1 inverted. But look at if this time is the input to have a change, a sudden change, and your output is not respond immediately. So suppose to have low input, you expect high output. But the high output will not be ready until at some moments, such as this, being high enough to be high level. And this high level will be responded to in the low level. So there's delay in fact from here to there. So if at this moment your output is not high enough to be high level to respond to low level, so this is not ready to use. So you have to wait at this moment. So at least this is the delay. Of course, they have different definition. Now we just talk about genetically, evidently, that the output you have to wait for output to be ready. So this delay. So then, of course, you know the delay. Then matter is that how to estimate this delay. In Elect 273, we talk about RC circuit. If you have such waveform at input, you have such waveform at output, so you will have also same delay. So delay is one indication is tau related to product of RC. As we talked about previously, what do you mean tau? Tau means after tau time. after total time, you ought to but rise to 63% of the amplitude it is supposed to be. Not completely, but complete most of them. So that is tau mean measured by R and C. So if you say my following circuit have to have a full amplitude to be operated normally, so you have to wait even more than 2 taus. So if your following circuit or circuitry has a lot of tolerance for noise, they're able to take 60% or 70% amplitude as good enough to make the following stage operate normally. So your delay will be 1 tau. So anyway, you have delay. So as we discussed previously, this tau is RC constant, and because it's charge-discharge process of this capacitance, and R determine how strong current, and C determine how fast the charge accumulation. So determine how voltage is built up, how fast. So both are important. So this is RC circuit. Now we come to digital electronics, a digital circuit gate. So this is not a matter of R and C, but the C is still there, true, the same as C. And we have spent so much time to talk about how to estimate this C, because C is not purposely given, it's just parasitics, naturally full. So spend time to estimate C is important because C will determine your speed and power. Then R, there's no R, no explicit R. But even though there's no explicit R, but we still have channel resistance. And unfortunately, this channel resistance is variable with the voltage. So now I'm going to discuss to show you what is the principle we use. Doesn't matter, you have so many different forms of circuit, but estimation of delay, how much time you need for this change from this state to that state, and what is principle. And the same principle can be used everywhere. Time constant can be used only in RC. It's not really precisely applicable in this kind of circuit. So what is basic principle applicable universally? Good. So first we start with a capacitance. And you have capacitance. You must have some connection. This is called VC. And the current flowing into charge it called IC. IC, we know that, as I said, one of the most important equation or formula in electronics is IC equal to C dVC. As long as you have capacitance, doesn't matter where the current comes from. This is always applicable. And very easy, you just talk about, then I switch the position of equation of IC and dt. So you get such a thing, C, dVC, IC. So equation is the same, just to change the shape, change the form. And normally, this IC, the current doesn't matter in this case or in that case. The current must be related to VC, must be a function of VC. In this case, IC is equal equal to, if VO is VC, because cross the voltage cross the capacitor. This IC is VI minus VC divided by R. In this case, in this particular case, IC must be function of VC. Must be related to VC. Doesn't matter C is, both dependent or independent. So IC must be related to this. I'm not talking about C. C is self-different. So this equation comes to this equation is normal. Just they are equivalent, or they are identical. So we have a condition, for example, if at T1 you have VC equal to VC1. At T2, VC equal to VC2. This normal, like this case, T1 is here, T2 is here. Then you can easily to see T1, T2 interval dt equal to C dVC IC VC IC of VC. This is also the same equation. However, the two boundary point in the right side of the equation should be VC1, VC2. Corresponding time boundary is T1, T2 is normal.
The time boundary is not the same as tau, right? It's different.
No, I'm talking about general. Okay. Good question. So this is VC waveform. Any general during transition. If this is T1, this is T2. And this point is VC1. That point is VC2. And as I mentioned, if you have large IC, this VC, change from VC1 to VC2, you need a shorter time. Or if you see it smaller, the time will be short also. So this is start from the general equation, and this is delta t. If you have delta t equal to T2 minus T1, so left side of the equation will be delta t. Right side of the equation, minus T1. Right side of the equation, just general equation that we use to estimate the delay. In fact, I just write every detailed step. On one step, you're able to find more details. So this is an equation for delay estimation in general. Only to confirm one point is delta t is proportional to capacity. Large capacity, you need more time to make the change. Delta t is inversely proportional to the charging or discharging current. So repeat from different angles to confirm the same point. As I say, tau is applicable only for RC circuits. Whereas this one, I didn't specify anything. It's general, the generic, applicable everywhere. Only difference is we have to make sure that what is IC, who provides the current. This current is constant or is varying?
Variable.
In most cases, varying, yes. Only very specific constant. For example, if I say the current is provided by current source is equal to I in this particular example, then it will be very easy. That would be the easiest case. If in this case is constant, 2 amperes, then your delta T will be equal to C V2 VC2 minus VC1 divided by I. That will be expression you're looking for. Because this is constant, you can move to the outside of integral. And then will be integral of dVc, VC2, VC1. So this will be, so that will be C delta V over I. Now,
this is the lead estimation as single node, right?
yeah, single node.
Okay, that's not between.
Single current, because, so this is the easiest, most, simplest case. Normally it's not that. But in very often case, we try to approximate it. It's one case. In another case, so if in such a case it would be very easy. But unfortunately, it's not that easy. Just and say this IC is from 2 currents. This is I1, I2. Then IC would be I1 minus I2. So you have to count both currents. So things become more complex. So important is to find where IC come from. If IC is easy, it's simple, just easy. Otherwise, it will be very complex. So it is from this single node. You're right, single node. But this single node may have only one branch, may have multiple branches. So if multiple branch, you have to use Kirchhoff's law to find, like in this case, this only single, but still 2 branches. Now come to this example. So I'm talking about principle, and this example, how to deal with. And qualitatively, we know the waveform output must be like this. Only difference is this transition could be faster, could be slower. Depends on current. And of course, the current is proportional to the size ratio, WA. And we know that now. If we increase size ratio to have stronger current, but will make capacitance at this node larger, and make heavier load for the preceding stage. And the first, we just using all the knowledge we acquired previously. So you must have transition for, because VI switch from 1 to 0, and VO switch from 0 to 1, you have transition. After transition, if you give sufficient time duration in this period, between here and here, so your VO transition is shorter than this period, so you must have a certain time the circuit in so-called steady state, DC steady state, because it reaches highest level. So one principle is that this duration should be longer than its transition period. This is common sense. Number 1. Number 2, your voltage, when it change, then reach steady state. This is voltage, but your current is in such a way. in such a transition period, your input is changed from high to low. Like that. So case of CMOS inverter. What the condition? If Vi is ideal square waveform, so what means square wave? So just like you have no time, means your Vi change from high level to low level all sudden without for time. And change from low to high all sudden without rise time. In reality, impossible, just we assume to simplify analysis. So ideal waveform, as we know that the voltage cannot not jump from one level to another level. So we assume it does jump, it did jump. Just to simplify the case, if you have such, and then I will put in such in this transition. So I will copy this from VDD to 0. And of course, before this moment, your circuit already reached so-called steady state, 0. Output input is complementary. Input high level, output low level. Now, input change become 0. So how output change? As you know, it goes slowly from 0 again to VD. Other condition, if input change not very fast or remain 0 but for a long period of time, long enough for the circuit to finish transition period. So one important thing is that my question is, during this period of time, during this time window, your Vi is 0 and remain 0 unchanged. In such a case, the equivalent circuit of this circuit and of this inverter would be 0 make NMOS off, 0 make PMOS on. So equivalent circuit is over the period during this time, 0 and off. So your inverter is reduced to that simple configure, simple structure. Because one of them, NMOS, is not active, is off. So this is circuit applicable during this time window. Now let's look at the current. So what is current? Charge or discharge? Capacitor. And of course, NMOS has 0 current because it is off simply. PMOS may have current because it is on. So how current changes
when the NMOS closest reverse.
NMOS of forget it, as if does not exist during this time window. So PMOS, how PMOS current changes. So first, I will say IC equal to IP during this time, over this period. So simply I put IP here. IN is 0. So now is P current from N PMOS dominant to charge the capacitor. And I sketch diagram to show it is initially very large and then reduced to 0. So qualitatively, you should accept it, because why? If this is moment, it becomes steady state. So steady state normally, of course, doesn't matter from which aspect to understand. You always have IC equal to 0, because DEC is 0. So in this scheme, of course, IP is going to be 0 in steady state. So it is reasonable during steady state period, you have IP equal to 0, IP equal to IC equal to 0. Then before this, you have transition time. Based on this scheme, you say the PMOS is only device that's possible to provide a current, because IN equal to 0. And it shows at the beginning, IP is pretty strong, and then reduced to 0. Reduced to 0 is expected. But from transistor point of view, what happened inside the transistor, PMOS? From transition DC steady state point of view, you say this must be 0 at the end. Waveform must be like this. But what happened in transistor? So let's look at. So a little detail. If this is T1, at the T1, or TA, not confused with general T1. At the TA,
Goes to saturation.
She says saturation. Do you agree? At the TA, it's a PMOS in saturation. What do you think about? What's the reason for saturation?
Because the capacitor voltage is low and the
Very good point.
VDD is high. The difference
at this
is
moment, he's right, because if you look at the waveform, at this moment, if VI already jumped down and 0 watt is already applied, but output exactly, this voltage cannot jump suddenly. Even though we assume input is ideal, but even ideal input, output cannot be ideal. So output is still at the 0 point. So this VDD, this is 0. You still have VSD for PMOS is equal to VDD. This point minus 0. And meanwhile, of course, you have VSG for PMOS equal to VDD. This is during this time window, within the time window. Which means what? At this particular moment, this is drain equal to 0. This gate also equal to 0 in saturation. Right. If saturation VSG for PMOS within this time window within the time window, you always have VSGP equal to VD. Because here is 0, there is VD. So you always have operating points find along the curve. This is at t equal to t starting point. You have voltage equal to V for VSDP. So this point, so now should be this point is t equal to TA. You have VSDP equal to V. And this corresponding to, under the condition, corresponding to the highest IP under the condition. So this voltage current value at this point is the highest point this transistor PMOS can reach. And this can be calculated under saturation condition.
Could you re-explain why VSDP is equal to VDD minus 0?
At this particular moment, here, your VO at this point is 0. And this is VS, source of PMOS, is VDD permanent. So difference between the two is VDD. So.
Yeah, okay.
One is important, during the entire time window, within time window, doesn't matter which moment, you always have this true. Because the data always 0. At this point, it's always E. So this is operating point at this particular moment. And that corresponding to the highest current amplitude, saturation point. So then if T is greater than TA, at this moment or that moment, and so on and so forth, a little later than this moment. And this IP is charged, so bring voltage up. Then you must have VO greater than 0 because charge accumulated. That means VSD for PMOS is reduced. Yeah, you're right. This is equal to VD minus 0. VO is reduced. So reduced, you should expect the current reduce. The current IP is reduced, is reducing. So that's why you see the waveform. Yes, you see the waveform, current is reducing. So this amplitude is the saturation current amplitude. So you calculate according to VGS, VSG minus VTP, whatever. VSG equal to VDD minus VTP square, whatever. Blah, blah. So then you have VO increasing, VSDP decreasing. And if you want to visualize how the operating point is shifting over the time, it's shifting this way. And then your IP is reduced. is strong in saturation mode, then VO charge up quickly, so you can see the slope. It is the beginning segment is pretty strong, but very quickly, your VO is high enough to make a VSDP small enough to be in trail, and current reduce, as you see from this curve. Current reduce, then increasing of VO is slowed down, but still increasing. But the rate is slowed down. So current reduce also. So that's why you have, if you, I hope you can see, you can see, even though the waveform is sketched qualitatively, but in normal case, you must have current or jump at the very beginning, pretty strong in saturation because PMOS in saturation, and maintain relatively stable in very short period of time, stable current level, because this is during saturation time. And VO quickly increase. In other words, VSD quickly decrease and quickly go to trail. Then you have strong, small current. This increase is much slower in the late section than the beginning section. At the end, it will reduce to 0. So at the end, our transit period, you have IP reduced to 0, but the PMOS is still on. IP reduced to 0, but the PMOS is still on because VSGP still equal to V. So this, as I said, this equivalent circuit applicable during entire time interval, in a time interval. Any question?
How long it will be in saturation? The percentage, is it 63% you have told about previously?
Okay, let's say this is point between saturation and trail down. So during a very short period of time, your voltage change from this point to that point. VSD reduced from this point to that point. Initially so big, then at this point reduced too small. So small, because it is up. So you can assume during this period, the current is almost constant, pretty stable. You can use this equation to calculate
The time.
what is delta T. So during this delta T, this current is equal to I. This I is almost equal to saturation current, which is VGS and VSG minus VTP square multiplied by W. And what is this point? At this point, if I say this point is, say A, at A point, it's between saturation and trail. So you must have VSG for PMOS minus VTP value equal to VSD for PMOS. This is equal to VDE. This is equal to, must be given. So you can find this point, and delta T will be VDD minus this point.
Which one is given?
Sorry?
Which value is given?
VTP is given. So this point you can find it yourself. If you want to find what is duration of time duration during which the transistor is in saturation. So if this point, can you see the very almost faded line here? This is corresponding to the point I showed you. What I should important is that it has a peak current. For BSF design, this is important. What do we mean peak current? Is maximum current just transistor needed. Number one. Number two, it has if you look at this period, even though sometimes current is stronger, sometimes current is weaker, in some time it's zero simply. But over this time window, you must have average current. You write down. You can calculate average current. So statistically, these two currents are important. One shows peak, the other shows average. And because average current will show the shape of, reflect somehow the shape of instantaneous current.
Also, average current is related to power dissipation, the total power dissipation of the circuit.
I'm going to talk about this tomorrow. So, if you really manually to estimate this delay, how much time you need from here to there is pretty complex, even though it's very simple case. But the manual calculation is complex. So now we use simulation to find. But calculation about peak current is not difficult. As you know, this is saturation current of pins. If W over L given, VTP is given, VSG of PMOS is VDD. So pretty simple. But this is characteristic voltage level we will use. And this is the first scenario during first time interval or time window. If then the second time window, if assuming they are different, during this period, you can figure out in that time window, it's just opposite because input is simply VD. And output response to this jump will be reduced to zero. And the principle is the same because just opposite, instead of PMOS active in the previous period, now is high input make PMOS inactive, disconnected. NMOS active is VDD at the gate. And you have capacitance there. And the current is provided by NMOS. The IC is minus IN. The same amount, but in opposite direction, because we assume IC is the current towards the capacitor, the charging current. But in this period is discharge. So it has a minus sign. And voltage reducing discharge. And the principle is the same. From IC point of view, the current is negative. But from transistor point of view, because negative, it is going other way around. It's opposite to its assumed condition. And it NMOS make discharge. And the same, at the beginning, the current pretty large. Same principle, because at the beginning NMOS is in saturation and then in trail. The reason NMOS in saturation at the beginning, because it is initially high level here, then reduce discharge. At the end, discharge to zero, so VDS will be zero. Same principle. But what happened in PMOS in the previous time window, now I go to NMOS. So that is all the story is that in this case, IC is provided is come from NMOS or PMOS, and transistor current is not resisting current. And then it's not simply like an RC circuit. You have C there, but R is not explicitly presented, but still, as I say, not explicitly like a resistor, but still it's current flowing through the channel. So channel resistance make a difference. So if you make W over L larger, I hope you still remember, if W over L larger, current will be larger. From channel resistance point of view, it's opposite. Channel resistance doesn't matter if it is linear, non-linear, it's always proportional to, the resistance doesn't matter linear, non-linear. It's proportional to L, inverse proportional to W. Applicable for transistor channel 2. So you make W over L larger, resistance gets reduced. So this is get the same principle. But it has non-linear features, so that means in saturation range, we may use this kind of equation to simplify estimation, but in trail it's a little more complex. So current is variable, then calculation becomes complex. Any questions? So this is a time estimation concerning a CMOS inverter. And I think very important is to know that, maybe I use this one, to know that what is the peak current, how to estimate it. It's very important. I say important because. And then another important issue is, if you look at this example, very simple one, if for charge discharge, of course, charged by PMOS, discharged by NMOS. But if you look at from source point of view, voltage source point, because everything energy is from the voltage source. From this point of view, if you have a CMOS inverter or CMOS gate, this VDD source, you need to charge this charge. You must have current flowing from the source. And this source, if you connect alone, I think at the second time I talk about. And this current is equal to IP, right? So if this is black box, I look at how much charge it takes from the source. So this is constant IP. And the peak current on this point is same as peak point at that point. So this is very important. number one. Number two, as I said last time, this is you stand alone. If you have several like this, many like this, so what peak current here is the peak current of all of them, all connected. If you have million connected, then multiply by million.
If they're the same.
If they happen to switch, the transition is simultaneous. If transition not simultaneously, then the peak current is not like this, because if this is at peak, the other is just sleeping, no current. As we see, the current happens only during transition. So assume you have two. One is transition at this time, the other is at that time. So the peak current is not twice of this amplitude, it is the same amplitude, but they do not transition at the same time. So this is very delicate issue. So that's why we talk about activity rate coefficient less than 1. Okay, this is then some people ask, you talk about CMOS inverter. So what happens if CMOS gate, you have pull-up network, pull-down network? So in this case, we are very simplistically like different way of simplification. Simplification is not simplistic. If we do simplification simplistically, this is a lot, a lot of approximation, not accurate, but sometimes is acceptable for certain degree of approximation. If you have inverter, we know how to do it. If we have, for example, a gate, a NAND gate, you have A now. How to do with analysis of delay estimation? So normally we make a counter equivalence to equivalent this part into a single equivalent transistor with equivalent W ratio. And this part to this equivalent. This is N, and this is P, and this will be N equivalent. So in many cases we do this, but this is not only way of doing simplification, but pretty often we do it. So this simplification is pretty simple. If you have two in series, say WL, W1L1, W1L2, then equivalence will be W1 over L1 plus L2. So this will be converted somehow from for analysis point of view, not from function point. Analysis point of view, the two in series will be equivalent to a single transistor for calculation. And its equivalent WL side ratio will be equal to this. And since you already have idea how to do layout physically, and I think this is pretty easy to understand now, because this one can be equivalent to, if this is this one is top transistor, this dash is poly, this is P diffusion, then second can be made in this one. Okay. So this two transistors corresponding to this structure can be equivalent to this combined to become one transistor. So this is L1, this is L2, so this is L1 plus L2.
But your inputs are combined also.
This will, the reason to do it is that if you know how to do a inverter, but I didn't tell you how to do the estimation for analysis for the gate. So for analysis purpose, you can first convert a gate pull-up network, pull-down network into a so-called equivalent inverter. Then you can make analysis in this inverter and say this is a delay estimation for the gate equivalent.
This is only for delays.
Yeah, for delay estimation. In order to do more objectively, so your conversion should be reasonable. Like convert this structure, assuming is same as that structure. And that structure is single transistor. If they are in series. Then what happens if they are in parallel, like this one, these two?
The opposite.
So that, because if in series, you have no other choice. If you estimate the delay, you must assume it is on case. If off, forget it.
Is W by
Current
L1.
disappear. And there's only, for this structure to have a current, is only both on. But for this structure in parallel, if you have current flowing for discharge, it can have multiple scenarios. In scenarios, this on, this off. Another scenario is this on, the other off. And another scenario still is both on. So if in parallel, we'll take, assuming this is W over L1, this W over L2. So W over L equivalent in parallel case, not series case, I put 2 dash as parallel. We'll consider as minimum of W1 L1 and W2 L2. Why it is minimum? Because smaller case, if assuming these two are different size, if this is smaller, this is larger. If this is on, off, this is on, and have smaller current. And that will be for delay estimation. Smaller current is worst case scenario. So that's why we take small. Yes.
So the width of the two transistors, should be equal, right?
If equal, doesn't matter which one, but
Yeah,
worst
but this
case.
should be equal, just like what you do
We
previously.
talk about this or that.
The
This one.
MOS.
Yeah. So that means if you have discharge current, discharge can through this one without that, or through this one without the other one, or both on. So what is the weakest discharge current scenario? Is the smaller transistor is on, the other off. So the equivalence we take the worst case scenario.
Worst case. Great.
Weakest current case. Weakest current means the largest delay. So this is kind of very simplistic, but useful in delay estimation. In case of gate.
Yeah.
You had a project simulation, and in your lab or in graduate class, you have second or first simulation reports you have observed. And this kind of waveform you have observed many times, I guess, huh? So will not be surprised. So always, if a CMOS case, you always see the current during so-called transition time. And if the input frequency is low enough so that you have sufficient time for each transition to finish. To finish, then you have period, the input current, and the current of transistor is 0. So one thing I would like to mention that this IP current, in this case, I show the current of charge discharging. That is IC. I show the current of IP because this current is important as I erase down, because this current is directly from the source. And the source line, you decide how wide it should and relate it to this current, because each current makes contribution to the total current flowing through the line. But the average current, so from this point of view, average current, how you estimate? Assuming this circuit is standalone connected to the source, then I ask you, what is average current taken from the source? In the middle, yeah, right. So if you do simulation simple, you use a tool in the waveform tool. There's a calculate. They calculate average current for you. So you have to specify during which period you take average. If input is like clock periodically, so you take one period is good enough. Or doesn't matter, take 10 periods, it's the same. Yeah, but if input is not periodic, just like a real digital signal, you have successively zeros and ones randomly. Then you have to take a period long enough to be statistically correct, and then take average current. But in this case, you say this period is 1 cycle time. And this average current, I think in this level, because most of the time is 0. So this is important. And then we talk about, like, this case is always normal, generic so-called delay, because I talk about how to estimate phase and from this point to that point. And but in fact, the delay has different versions of delay. So just give you some idea about how delay is defined. This is, if we take the break. How delay is defined. So in normal case, it is very, I think you already know that if for a not ideal, not square waveform of digital signal, so you have normally rise time 4 times. And if not otherwise specified, the rise time is count a voltage point at 10% point level. And then another point is 90% level. The time required for this voltage to change from 10% of level to 90% of level. This required time is called rise time. And four times is opposite, 90% voltage level to 10% voltage level. So this is default conventional rise time, four time definition. Some students may ask why you need to say 10%, 90%, not 20% or 30%.
Because it will not switch the circuit. It will not switch the circuit.
Yeah, this is conventional. Why not say 95% or 98% or even 100%? Because you can see that as we give the example, the transition at the end is very slow because current reduced to very small.
So we mean like the saturation point.
Yeah, it's very small. So, but for the usefulness of the voltage level, you don't have to wait at 100% level. Reach this level is usable, good enough to be used in most cases. And otherwise, this time is you wait uselessly and it rises very slowly from 90% level to 100% level. So that's why we start. We end at 90%. 10% are similar reason, very practical reason, because initial time could be very small, could be very slow, could be very fast, could be very slow. So we just get rid of the two.
Is it possible to have like overshoot and
Possible. Sometimes overshoot is very critical. It's disturbing. They're able to low pass, cover overshoot. I'm talking about normal. Normally, digital circuits overshoot is not really bothering. So we do not really take care of this.
if it's a high-speed circuit and you can't put a low pass because it's going to introduce more delay?
True. Low pass, high pass is relative. If your bandwidth is 1 giga and 100 megahertz is low pass, it's relative. And this is rise time, fall time is concerning only one voltage signal, does not concern two. But as you say, if you have input here, output there, this concerning two, because as we just see previously, is more like two waveforms. I talk about delay is input as reference point, and then locate output to when it is usable. And this is called delay. Delay is somehow must concerning two waveforms, not a single one. So delay is also called propagation delay. Just like this one. The previous example show input is idealized. But this is input and output both in reality. So input like this, for good purpose, you get output like that, just opposite. So what do you mean delay? So precisely define the delay depends on the circuit, but by default, there's a kind of convention. Not necessarily follow the convention, but without otherwise specified, we follow the convention. So delay is when input started to change, output followed. This is called the delay. So how to define the delay? So-called propagation delay is that your reference point, the starting point is half of the amplitude, 0.5, 50% the point. Corresponding to that time points, we call the T1. And output responds, and it does not respond immediately, but after a certain time, it also reaches 50% of point. We call it T2. So difference between T1 and T2 is called propagation otherwise it's flat. And this is concerning specifically for output change from high to low. So this delay is called TP. P means propagation. HL
I think.
from high level to low level is output side, not input side. And if input is change high to low, output go to opposite from low to high. Similar. This middle point is starting point reference, T3. And then when output response reach the half amplitude is T4, is respond time. And the difference between T4 and T3 is called TPMH.
That's
So-
also a propagation delay.
Propagation delay.
They're both.
You have two cases now, because in rise and fall will be different response. As we know that this rising depends on PMOS current, mostly, and the falling depends on NMOS current discharge. In most cases, they are different. Maybe difference is small, but different. So that's why you have TPH or TPLH. So this genetic definition is not applicable for all the cases. So they say it's 50-50. Some case may be defined fall down, TPLH is not half, but lower, 30% or 20%, because they think this is not usable. You have to lower a point will be usable. And TPLH would be higher point. Depends how you use it. So there are two different concepts, as I say. Now, propagation delay is related to waveforms, whereas rise time, fall time is the single. And I show here example. Say if you have a digital circuit or a block of building blocks. This is a building block including multiple stages. The input like this, output like this. And this shows rise time, fall time, not necessarily the same thing as propagation delay. So input on normal case, not ideal but pretty good quality of waveform. Output also pretty good quality of waveform. Rise time, fall time very short, at least relatively young. But it does have a very visible propagation delay. TRTF is small, the delay is large. So TF is very short, but delay is T1, T1, T2 is pretty significant. This is very easy case, very easily see case, very common case. Because in most cases, you have multiple stages in the block. And you can spend the last stage to shape the waveform. So output the waveform will have nice shape. Short rise time, short fall time. But in this case, you must have multiple stages inside the block. So propagation delay is still large. Normal case. Okay, this is about delay thing. Do you have any questions? If not, we will take a break. Thank you.
How long the propagation delay can goes on? How long?
How long depends which circuit.
Yeah.
If a large circuit, if a small circuit gate and propagation delay is very short, It's below nanosecond normally. And your simulation, you can see it.
Yes, picosecond.
Yeah.
48 picosecond is a falling delay, and the 149 is a rising delay.
But a large block, this is and I would say large block, just say if you have clock generated in one place and then sent to everywhere. And a block, a gate close to the source, you have small propagation delay. Because the wire itself is already introduced a delay, unlike a tau. And then if this circuit is going to apply to next stage, other stages, then there's accumulation delays. It could be very large.
So there should be a minimum number of transistors in that block, so that the delay should not exceed the cycle.
Yeah, this we wish, but never make it. It's a minimum. You must have your design function. You must have a certain number of gates. So delay stage by stage, accumulate. Yeah. Questions? You don't have to be. Yeah, it's true. Normally we make it equal. But it could be.
Areas gravity, how long the source origin.
Yeah, and the reason is
That one.
I didn't understand. This is which material?
So this is
it's wrong. Am I just doing it wrong?
Oh,
Which material?
one is great, the other is I may not see it on the second one, because I think that for the full voltage right at one.
Okay, you talk about this one, because I try to understand your layout.
Sorry, I was like, I thought they were okay.
so I mean like
Okay, this is, if this is connection of metal.
I mean like this
Yeah,
is
you
It's just the eighth one with the area thing, I don't know.
You say, okay, now it's W over L per
Is a
equal.
big factor, but.
so I mean I
No,
don't
not just
mean
with
the
it, because
base
for all,
of
okay, so because of the area also.
Yeah,
because
can
of
be,
the
but it
materials
can be
are-
different.
We also
Yeah,
know
but
the depth
if you
is.
mean say like this, so this is the width of this.
I put this,
It could be also
because of
different.
the area.
I can tell you the
And
width.
then I put poly is more elevated than diffusion.
If I make such a transistor, like this alone,
Yeah, it was very, like the picture was a bit confusing.
they are different.
It's one of those trick questions, I hate. It's
This
like technically the answer is yes, but I know it's, that's all the same.
Yeah, but like
You
because
can-
this is a
you can-
series, so it's like this is make one
Most cases, yes, we but I'm talking about generic case now.
Getting the right answer for like.
Course, general case, they should be equal.
They can be different.
So like for example, usually
Yeah,
can
they can be different.
you expect to make them equal.
No, you don't
I
have
think it was
to.
wrong.
View is wrong just because of the justification.
In general, it can be different. But
But
in conventional, we like convenient to make it equal. This is
তুমি
true.
ঘুমা তুমি যাও না আমি ঘুমাচ্ছি আমি একলা জিজ্ঞাসা করতে পারি না তুমি কালকে যাও না কেন? কালকে যাও না কেন হ্যাঁ
আবার ক্লাস ছিল
এর আগে তো ল্যাবে ছিল
ক্লাসের আগে ছিলাম আর ক্লাসটা মিস গেছিল
কোন ক্লাস
সফটওয়্যার ইঞ্জিনিয়ারিং সব ক্লাস মিস
বুধবারে ক্লাস থাকে
Did you get the?
সাড়ে 5টা বাজে তো আমরা তিনটা থেকে 5টা পর্যন্ত থাকতাম
So what do you do for extra?
আগের ক্লাস কেমন আছে
Yeah.
আগের ক্লাস ল্যাবে ছিল
I think I was supposed to.
So which kind
Okay.
of?
I got 4.8.
পুরোটাই করো নাই
অনেকক্ষণ হয়ে গেছিল তো পুরাটা নয় লাস্টে গিয়ে মাঝখান থেকে ক্লাসে ঢুকলে বোঝা যায়
ইয়া তো রেকর্ডিং দেখিনি না
রেকর্ডিং প্রসেস দেখা হয় না।
তোমার
So this, but in this
Ah,
case, they
তিনটা course
will
আছে
up
আমাদের।
imperfect level, but this
Home quiz শুরু
this
করবে?
imperfect
কালকে
level
কালকে ইয়াতে
হোম ফাইনাল শুরু
final result.
না
ধরবে এখনো?
So you do
পরীক্ষা দিয়ে
logic
তারপরে
is
অফিসে গিয়ে অনেক পড়াশোনা করো
আজকে
four
একটু বলি।
Yeah.
and so this is C odd
And how about?
Like having a full on
English
this.
logic you have.
She jumped two of the worst.
No, actually, the third case I found on the RTT.
Yeah.
She said that she dropped two of the worst quizzes, right?
They use
পিডিএফ এখনো পড়া শুরু করো
No,
না?
no. This is how
হোম ফাইনালের জন্য পড়া শুরু করো নাই পিডিএফ?
pretty sure.
চেকের সলিউশন দেখো চেকের সলিউশন আছে নাকি
So the zeros for other
ওটা তো টাকা দিয়ে
So actually, they do not even complete what that what
All your
So,
quizzes are like
খুঁজে
fire.
দেখো
actually it is right.
গুগলে খুঁজে দেখো
So here,
তুমি পাইছো?
আমি দেখছি চেকে আছে
সেটা তো তো কিনতে হয়।
কিংবা
so
এক
F4,
মনে করো তুমি 8 ঘন্টা কাজ করছো হ্যাঁ
the
2 ঘন্টা
output
2 ঘন্টা বাদ
when it is 0 1
দেখবে
or
যে চেকের সলিউশন তোমার সামনে স্ক্রিন না কি নেই
0 when you have 1 1
বসে
So
বসে
if this output 1 is
তুমি
the
3 নাম্বার দিয়ে বলো
the A and B is on the
So what
one.
it means that I'm curious. What means that?
Yeah, so yeah, as I said.
আমি তাহলে তোমার দিব না
This is for the project.
This does not make sense.
কিনবা?
না কিনবো না
Oh, okay, I see.
কেনার পরে পরে দেখলাম এটা ওইটা না থেকে
Did you see this one?
তুমি দেখতে হবে কারণ
This is
ওর
kind
তথ্য
of like this.
সে দিয়ে দিতে পারে আমি দেখছি কয়েকটা পাইছি তো 2-3টা জায়গায় দেখছি সলিউশন কিন্তু নিচে নামতেছে না
প্রজেক্ট শুরু করছো? ডিজাইন সিস্টেম
ডিজাইন সিস্টেম না এখন শুরু করি নাই কালকে থেকে বলবো না
Okay, yeah, this I
ডিজিটাল
saw.
সেটটা শেষ করা
Yes, and the design. So
ডিজিটালে তোমরা কি করতে পারো বলো তো?
Yeah, they count
মানে সবাই এক একটা ব্লক দিচ্ছে
হ্যাঁ
ভাগ করে দিচ্ছে যেমন আমি মাল্টিপ্লাই একটা ইয়ে
তুমি
আমি
আমি তো মাল্টিপ্লাই নিছি তুমি মাল্টিপ্লাই করে গেছো
না এখন শেষ করি নাই ওই সেদিন ডেমো একটা ইয়ে ছিল না প্রেজেন্টেশন ছিল না
হ্যাঁ
ওইটা দেখার পর কিছু মানে কিছুটা শুরু করছি আমি ওই যে এক শিফট মাল্টিপ্লাই সেটা দিয়ে করছিলাম কিন্তু ওটাতে আরো অনেক কিছু একটু চেঞ্জ করতে হবে যা করছি ঠিক করতে হবে এখন আপাতত
ওইটা আমি আমি
টেস্ট বেঞ্চে
আমি আমি বিবেক বানসালকে জিজ্ঞাসা করছিলাম যে যদি একটা বিটকে আর একটা বিট দিয়ে মাল্টিপ্লাই করা হয় তাহলে এটা 16 বিট হয়ে যাবে 8 বিট ইন্টু 8 বিট 16 বিট আবার আছে a স্কোয়ার আবার 8 ইন্টু 8 20 তাহলে কত 24 বিট হয়ে যাবে তো 24 বিট হয়ে গেলে দিক দিয়ে 1/4 1/4 ভাগ করার পরে কত হবে কমপক্ষে 21 বিট তো হবে কারণ 4 মানে কত 1
সরি 3 বিট
4 মানে হলো যে 3 বিট 111 মানে না 011 011
100 হচ্ছে 4
101 101 মানে 4
101 হচ্ছে 5 1004
This okay.
আচ্ছা 100 হলো 4
Oh yeah.
4 হ্যাঁ 4 100 তাহলে 100 করলে 3 বিট কমবে 21 বিট লাগবে কমপক্ষে
কি বলবো
মানে কমপক্ষে আউটপুট 21 বিট হবে
This A
যেমন তুমি ইয়ে করো এক বিটকে এক দিয়ে গুণ করলে এক বিটকে দিয়ে 8 বিটের সাথে 8 বিট গুণ করলে কত হয় প্রথমেরটা কি 0 হ্যাঁ তারপরেরটা 1 0 0 0 0 0 0 0 এইভাবে যাইয়া 10 হয় 16 বিট গুণ করার পরে মানে 8 বিট ইন্টু 8 বিট করলে আমি বিবেক বানসালকে জিজ্ঞাসা করছি কিন্তু এখানে তো আউটপুট বিটে দিছে তোমার কত মাত্র হ্যাঁ
as long as you write
হ্যাঁ তো ও কি বলছো কিছুটা
বলে যে I will give you feedback I'll come back to you মানে সে দেখি জানাবে
from the design point of view, I must say.
আমাদেরকে জানাবে ছিল কিন্তু আর জানাই নাই বলেও নাই
Yeah, the
Not
output
necessary.
the output is
Not necessary transist number.
1
Yeah, but the output is perfect high and perfect low.
Okay.
এর আগে
Okay.
বুঝে কত বেশি
I think the important
দাঁড়াও,
for
একটু
you
দাঁড়াও।
to check
One,
is easy
one.
cut.
Yeah, I checked, like, in theory, I
Okay,
checked.
চারটা বানাবো। তারপরে one,
Why are you writing one?
But I think
It's about digital system design and others. How is your quiz today?
The first one it was okay, but the last one I got I think the right answer. What did you get for the last question?
0.048 millimeter.
4.8 into 10 inverse 5.
0.048 millimeters? Is that micrometers? 48 micrometers? 4.8 times 10 to the negative 5, times 10 to the negative 5, right? Meters.
For the first one, I think all three of them is false.
3? Only 2.
Avoid in some pieces, avoid pieces.
How?
So design
It's easy to put all of them false. Just
No,
click everything.
no, yeah, you're talking about the say gate to body to
Gate to
body
body
to-
is independent, is voltage dependent.
body to drain and body to source is
Which one you put through?
The voltage independent one is supposed to be voltage dependent. And then the one where it says the area is because of the area, I put because of the area and the distance, but I think it's false. I don't know. I messed
the
up.
levels.
no,
I got half
they
of
are
the
they're
first
different.
question.
Okay, poly sub and body, poly thickness and sub. Okay,
Yeah.
this one is different, and that one is sub drain or sub source.
There's something between though.
Uh-huh. No, there is nothing between them because substrate
Oh,
needs
yeah,
P
yeah,
connection,
yeah, you're right, you're right.
ground,
So what's the
You're right.
and
Yeah.
from paper?
Yeah. It's a PN junction.
Now we have lowest power.
Final state phase representation, you can see the
Okay.
representation is the same as
So,
representation is just ABCD. State phase representation.
and then you have,
source and body.
this is LED, okay?
It was P or N.
So to visualize
এটা P ছিল না N ছিল? এটা কি P ছিল? N ছিল? তাহলে P. P কে গ্রাউন্ড করে দিছে।
এত কমপ্লিকেটেড চিন্তা ভাবনা কেন করতেছ?
এটাকে গ্রাউন্ড করে দিছে তো জেটকে গ্রাউন্ড করে দিছে। জেটটাকে গ্রাউন্ড করে দিছে।
কি স্যার?
তাহলে তো যদি গ্রাউন্ড করে দেয় তাহলে পুরো বডিটা হলো গ্রাউন্ড।
গ্রাউন্ড দিতে হবে না। কি হোস না? সরি এর হোস না? বডি
আচ্ছা বডি গ্রাউন্ড, হ্যাঁ বডি গ্রাউন্ড, ইয়েস ঠিক আছে আমি ভাবছি ওখানে আবার লজিক কারের সাথে ট্রিক্স খেলে তো আমি ভাবতেছি যে এই সহজ জায়গায় কোথাও ট্রিক্স দিতে দিছে কিনা।
and then this becomes 0.
এটা তো তার স্বভাব,
This goes
ছোট জিনিসের ভিতরে ট্রিক্স ঢুকে দিবে।
why?
লাস্ট পেজ
That's why.
হুম
Is this
লাস্ট পেজে কত 4.5 তুমি কত হয়েছো?
right? It's very okay. So this is better.
কিন্তু আমার তো সবই হয়েছে দেখলাম ওই কুইজের ভিডিও
এক্সপ্লেনেশনে ধরছে দাও।
এক্সপ্লেনেশনে তো কিছু ছিল না মানে অঙ্ক ছিল
আমি নার্ভাস হয়ে গেছি ক্যাপাসিটরের অর্ধেক লিখছি আর অর্ধেক করতে পারিনি। ক্যাপাসিটরের এরিয়াটা দিছি কিন্তু সেটা পুরা ক্যালকুলেশন বসে নাই। ক্যালকুলেটর নিজে আমার এদিকে তাড়াহুড়ো হয়ে গেছে। ক্যাপাসিটরের এরিয়া সিএফ ফ্রিঞ্জিং ক্যাপাসিটরে খালি লেন্থটা লিখছি আর বাকিটা লিখতে পারিনি। মানে আমি নার্ভাস হয়ে গেলে আমি আর লিখতে পারি না। তাছাড়া ইয়াতে ঠান্ডা লাগে যে হাতে, আমার টাইপিংয়ের সময় মানে টাইম ডিলে হয়ে যায়। টাইম যখন ডিলে হয়ে যায় তখন আমি আনসার করতে পারি না। হ্যাঁ কোথায় অসুবিধা?
কোয়েশ্চেনটা লেখা থাকে না ওইটাকে তো মডিফাই করবেন না, ওইটাকে কপি করে বসাই দেবেন তারপর মডিফাই
বাজি কোশ্চেনটাই তো তখন কেস স্টাডি না
there will be high level.
করতেছে কি আমি তো বুঝি যেটাই বলি সেটাই বলবো না
আজকেই করবো
আজকেই সব শুরু করবো না
আজকেই সব শুরু করবো
Without
গত 2 দিন ঘুমাইছি খালি
but now you connect this one.
And since
So you have to
আমার তো অভ্যাস আছে এই জন্য আমি কুইজটা শুরু করতে হোম ফাইনালটা শুরু করতে পারতেছি না
আচ্ছা
কিন্তু হোম ফাইনাল কিভাবে তুমি 2-3 দিনের মধ্যে শেষ করবা আমি জানি না
ইয়ে বলছো না ফাইনাল স্টেট মেশিন থেকে শুরু করতে বলছো না
but you permanently
But then you
আটত্রিশ
remove
না
it's gonna stay
34 পেজের
remove wire is not changing.
ফাইনাল স্টেট মেশিন মানে কাজে লাগবে বলছো মানে না
ওই পিডিএফটা করেই তো অ্যান্সার
My question is
মানে মিড এক্সাম কি ওইটার উপর বেস করে মানে হোম টেক হোম এক্সাম ওইটার উপর বেস করে হবে
But this one behind.
এবার না করে
because I'm trying to
তবে তার ইয়ে আছে নাম্বার দিতে চাচ্ছে সে কিন্তু নাম্বার দেওয়ার জন্য চাপ আছে
To supply this.
কালকে তো আবার ইয়ে আছে
Because you want to adjust.
সে ভালোই নাম্বার টাম্বার দেয়
but here you calculate the
তুমি মিডে কত পেয়েছো
You have to look at this how much you
তুমি কত পেয়েছো?
আমি আগে জিজ্ঞাসা করছি না
তুমি খালি আগে জিজ্ঞেস করো
আমি আমার আইডিয়া আসছে আমাকে বলবো না
90
not
হ্যাঁ
90
বরাবর 90 মার্কস পড়ে ফেলাইছি
and the same
মার্কস পড়ে ফেলাইছি উত্তর দিতে পারছি না
here also I set the login for 20 minutes.
So many applications we talk about
শুরু পাইছি কত 67 আমি পাইছি 50
আর বাকি ওই যে তোমার গ্রুপের ওরা দিবে
ওদের জানি না ওদের জিজ্ঞাসা করিনি
Okay, now we talk about
আমার
power.
প্রোগ্রামিং বেশি ভালো না প্রোগ্রামিং বেশি ভালো না
So this class talk about delay. I just have that you have basic idea about related to the design, in particular peak current, average current. So not really precisely go to delay estimation, just basic concept. Everything delay related to current. And related to current, not only the current counts, because current also related to safety of your operation in IC. And then, again, current also related to the power dissipation. So talk about power dissipation. Nowadays, the power is even more important from many points of view than speed. Because speed, we have BSI, we have 10 million, tens of millions gates in the same chip. So speed in not every cases, but in many cases can be improved by parallel, massively parallel process, improve speed. So since we're able to integrate so many gates in the same chip, we put a lot of units, processing units, to improve speed. But power, this is physically, you cannot go over. So I think many people talk about how to scale. Moore's law. Moore's law is artificial law, it's not physical. So say every year you have exponential increase of capacity of integration, blah, blah, blah. Moore's law is wonderful, but it's limited by physics. There's no choice. If you have small space, and normally chip space is like this, or even smaller. Count on millimeters. And if such a small space, your power dissipation will go over the limit. Power density will go over the limit. You are going to burn everything. Forget it. So if you're able to integrate many tens of millions gates in the same chip, but capacity to make, ability to make all the chip work, function, it is a challenge. Are you saying you can improve speed by parallel process? But if all the processes cannot active simultaneously, mean nothing. So power is even more important because safety, everything is included. So I'm talking about in basic concept, which kinds of power dissipation included or contribute to the total power dissipation. So number one is called static power. This we talked about previously. But this static power is not all the static power. And this is very narrow, just we already talk about. And we just talk about one of your classmates. DC current in steady state. I'm not talking about leakage. I'm talking about if your device dissipate power when input is not changing. Just like in your steady state. Input stays low, high level, low level. In this period, steady state period, if there's any current. If there's any current, not due to leakage, not due to somehow physically, is your design make it dissipate. This is called the steady. And theoretically, CMOS gates does not have static power. If the input is good level, we know if lower than VT and higher than VDD minus VTP, your current is zero. So static power is zero. But the pseudo NMOS is different. If input is high, so whatever you do, you have current. So we could talk about this kind of thing. So that we already talked about. Second is important, and we talk about state power is equal to current, static current, multiplied by VDD on this constant. Second, we talk about switch power. Switching is more like this. Just more like this. Just exactly this kind of power dissipation. If you have input pretty ideal, and then or rise time for time of input is very short. So you current provide a charge to build up a voltage if voltage needed to change from low to high or high to low. And this current is only related to the capacitor to charge it up or charge it down. And this kind of called switching power. This is power dissipation in dynamic case in ideal condition. Ideal condition or quasi-ideal condition means your input is very nice waveform, ideally square wave. Or the rise time for time is really very, very short with respect to the duration of the cycle time. So this switching power. So related to C, the load capacitance. So if this capacitor we quote individually, CL. L means load. As we know that this CL is very much related to what's connected. It's not major contribution from itself, from the succeeding stage, or from the wire. So how to estimate this kind of switching power? And if in such a case, it is equal to somehow related to two kind of things. One is peak power. Peak power, of course, is high peak. But in most cases, we estimate switching power is not really as specification. This specification normally is for the designer to do, but for user to do is more like average power. So average power, of course, understandable is average current multiplied by VDD. So what is average current? So this average current, as I mentioned repeatedly, is very much how much current you get from the source, from VDD source. Average current. So how to calculate? Of course, you can do integral. Integral of the period over t dt. And average. This normal we do this. But I would show you what I do as average current. So how to count? If we count the charge, I think I did last time, for such a period from here to here, half cycle time. During this period, the voltage changed from low to high, and then high to low, which means during this time, this gate or this inverter or this capacitor in particular will get a package of charge through IP, by means of IP, from the source. This package of charge, total amount, is C. This one you agree with me. Because initially, at this moment, the amount of charge in the capacitor is 0. At the beginning, is 0. Then you charge up to VDD. So amount of charge is VDD multiplied by C. So I put C is load, CL. So it gets amount of charge, a package charge to reach VDD. Then next time interval, it is released and thrown out to the ground by discharge. So if next cycle again, start again, it gets again this amount, then throw out this charge, and so on and so forth. So over the period of t, I talk about t from here to there. Over the time period of t, you get this amount of charge over t time. So average current is this. Current is equal to dq. So this is approximation, a good approximation. So if delta q or delta t, in this case, delta t is in this period, from here to here. And delta q is CL VDD.
And this is average current.
This is the average current.
And that's also
Over the period of t. Because if you talk about average, you must specify which time window. This time window is a cycle time, high to low time.
and it's equal to the integral.
Sorry?
It's equal to this integral as well.
Yeah. Now, of course, this is general. But But in our case, particular case, on the condition of this kind of input, and this is accurate. This is accurate. On the condition of square wave input. This is not approximation. And from other aspects you see, we use the principle and got it. I think it's easy to remember and much easier to calculate with integral. So this is the average current. So average power is average current multiplied by VD. So you have CL VDD over T multiplied by VDD become VDD squared. So this average power. You don't need to remember the equation because if you understand this one, this is it. And as I mentioned last time, normally we put R. R is between 0 and 1. Why is R? Because what I got is assuming input is clock cycle. Period. If clock input is not clock, it's just random digital signal. And you have successive 1 and successive 0. So you charge up throughout is less frequent. So if less frequent, then your average power calculation without R is very pessimistic. And in real case, it should be less. So put the R. R, you call it activity rate. If a circuit is not active, you can have two cases. Either you have successive 0, 1 a lot, and real frequency or real cycle time or effective cycle time is lower than, the frequency is lower, cycle time is longer than the clock. This is one. The other one is you design circuit, you don't need a lot charge discharge, so you make activity rate low. So if activity rate is low and you dissipate less power, means the circuit is not busy for charge discharge, it's less frequent. So this will be alpha 1 over T is frequency. CLV squared. So this is normally an equation calculation for the calculation of the switching power. So always the students, do we need to remember equation? I say no, understand principle is more important. So again, this is amount charge over the period to make average current. Current multiplied by VD is the power. Considering switch charge discharge frequency could be lower due to successive 0 or 1s. So you add up. That's all you need. Because this equation you can find in all the books.
How do you pick a value for alpha?
This is your usage. It's not easy. The largest is close to 1. So a lot of people to do research of low power design is very much try to find your circuit has low alpha. So let's look at if You say either you use slow time duration, means long time duration. You save less power, you dissipate less power, you save power. But of course, it's against your dense calculation. You want to calculate fast. So normally you cannot reduce it. Then you say, I reduce VDD so that you dissipate less switching power. But I say don't reduce VDD normally, because reduce VDD means reduce noise margin. The voltage swing less, so a little noise will make a negative effect. You reduce noise margin is the safety problem. You get more logical confusion in operation. It's not a good thing to do. Then you say reduce CL. But all the design try to reduce it. It's not much room you can make it. So nothing to reduce. Yes, you have to dissipate so much power. Then, as I say, many research try to say what to do a reasonable configuration for signal processing point of view. Building blocks can make same function, but let the gates switch less, reduce up. For example, some flip-flop, they have so gated flip-flop. What do you mean gated? Means flip-flop have a lot gates there. In particular, master, slave, flip-flop, whatever. There's multiple stages of latch, of inside. If clock is applied, you have D input, you have Q bar. So you try to make the clock is frequently switched up and down. But you do not let inside gate switch up and down with clock, but with D. Because in normal case, D change is normal data and will not be changed as frequently as clock. So you make control inside the gate or gates. Do not switch with phi, but switch with D. So inside switch charge discharge will be less frequent. As frequently as D, not as frequently as phi. So this is called gated clock. So it is one frequently used way to reduce, in order to reduce the switching power. So that is a lot of research there. It's not only research today, since we reached the all real level of very large scale, and people realize that you cannot follow the more. You have to follow the physics. And as your laptop, every time you get fan just make large noise all of a sudden. I think everybody can see it. Particularly in my new laptop, I think the design is not good. And that's because they switch activity too frequent. Get heat up. Switch power. So in practically, switch power, this part of dissipation you cannot really reduce. As I go one after another, each parameter, nothing can be reduced. Because you need to generate voltage signal up and down. You need enough amplitude, you need enough frequency, you need everything needed. Nothing can be reduced. Number 3 is called short circuit power. Short circuit power is understandable, as I mentioned, I think we mentioned previously. Say, if input is not that ideal, input is kind of thing like this. very terrible rise time, fall time, very long. So your output will be even longer. And during certain period of time, just look at input, inverter. Your NMOS, PMOS will both on. Because during this period of time, you're high enough for NMOS to be on, but low enough for PMOS to be on. So you have a branch of a component of current not going to charge or discharge capacity, instead of flowing from PMOS to NMOS, then go to ground and flow for nothing. Yeah, flow out, take the charge from the VDD, only percentage go to charge up, but the other percentage is flow to the animals for nothing and wasted. And this part of current make so-called short circuit current. Why is it called short circuit current? As I said, it flow from PMOS to NMOS, VDD to VSS for nothing, not contribute to the change of output voltage. And moreover, as channel resistance is a finite value, and this kind of current flowing through the channel and generate heat. So this part of power is really negative part. We try to minimize. But minimize is not easy now. So as I showed the other example, in the circuit, very often we do circuit, even we cannot eliminate delay, propagation delay. So we try to shape the waveform so that rise time, fall time output signal is short enough to improve the quality of waveform. And this is one way to reduce this one, because such input, such voltage, if applied to the succeeding stage, and will reduce the short circuit participation in the succeeding stage. So number 3. Number 4 is leakage. Power dissipated due to leakage. As I said, this leakage is not the same as steady power, even if it is still a current or power dissipation during steady state, during static operation. But the difference, as I mentioned here, is because design problem, because this is cannot really avoid. This, if you could make good design, should be avoided. So if you have steady power, when input is not change, and consider your design is not good design. But so the NMOS is different, because this is by using this input actually change, get some other advantages now. What mean leakage power? So just look at a transistor. If you have VDD at this point, you're supposed to have PMOS off. But in fact, it's not really off. Same thing, if NMOS you have 0, it's not really off. And because for one reason, your input is 0 level may not be perfect 0, could be 0.1, 0.2, and 0.3. It's low level. But for animals, may not be or for PMOS, so-called off states may not be really off. Means you still have small current going through this one. We call the sub-threshold current, means EGS is below the threshold, but does not mean you have zero current. So leakage current, number one, is due to sub-threshold current. Due to current is not really, the devices, when apply low level for NMOS, applies high level for PMOS, is not really completely off. You still have some current flows. So this is the leakage current. One of the elements. Second element is about diode. Reverse current. As we mentioned, doesn't matter NMOS, PMOS, you have source drain, each one make a diode, parasitic diode. And these diodes must be reversely biased so that the current is very small or considered as zero. But very small, considered as zero, it is not a real zero. And considering you have so many transistors, each source drain, source or drain is a diode. So you can count how many pieces of source drain, how many reverse diodes in this chip space, and how many reverse current. If these reverse current sum up, can be summed. So all these contribute to the leakage power. This is called leakage power. And this does not count for whatever layer, insulation layer broken down. This is not this is accident. This is normal leakage power, no accidents. So this is basically the categories of the power dissipation. So nowadays, till now, I would say still the biggest portion is switching power, and the short circuit power. Static power is only for very specific case, but normally we design to make it zero. That's why we mostly use CMOS gates, because this makes it zero is possible. Leakage power so far is small percentage, maybe 10%, 5% of total power. In normal chip, what do you mean normal chip means most devices integrated in the chip is for processing, not for memory. It's not, yeah.
And ground houses count as leakage power?
Sorry?
Ground houses.
No, not considered. Ground houses, as I mean, if I have time to talk about. So, leakage power is normally, as I said, substrate. That's due to most devices. And in memory space, it could be very significant. If you get job interview for memory design companies, don't say this is not important because they just hate it. And indeed, it is important because memory circuits devices are not active, just like your storage element, storage room. How frequent you visit here? So activity rate itself is very low. So if activity is low and these power relatively less, so this part will be more significant. So they do everything to reduce it. And as I said, initial ability to integrate more devices is all jumped like Moore's law predicted. Then also we have VSI. Also we don't want to put in the chip because so many things we can put, but want to put. So they put the memories for two reasons. Number one, we don't want to put the memories, okay. The other reason, also practical reason, because memory circuits have low activity, does not dissipate much of these powers. So we can make the chip operate. If everything is high activity in the chip, tens of millions of gates, then you get a problem. Too much power. So this is why leakage power is important for memory, and memory help to buffer the period we don't know what to do with so many. Like you lived in a dormitory, and next day they give you a house to live. Then what do? You don't know how to use the space. You put all the garbage. Okay. We talk about power bonds or ground bonds. And the power bonds, ground bonds, is anything related to these things or not? I think important to talk about one thing is unpeaked current. If you have so many devices, or so many gates, or so many blocks, with power, the supply of VDD through the connection, as I just mentioned many times, this resistance can be very small, just can be ignored, because the wire makes much more resistance than this inside the source resistance. So there's a large resistance here. Reach this point or that point is no longer VDD, but a VDD minus delta V. This delta V is a function of the currents. Not only one current, but summation of the currents. Sum of the currents. Because if this IP1 is IP2, and so on and so forth, how many units you are connected? Each time this gate is switching, like this one. Like this one, you get peak current during shorter period of time. And this current, because summation of sum of all the currents, the worst case scenario is all the gates switch in the same time. For this gate, you have this moment, you get peak current, and the other gates may be the same. And moreover, if the circuit we talk about synchronization, synchronized current, or synchronized operations, and you have a better chance to have a switch at the same time. So assuming you have n gates connected, the n can be 10,000, can be 100,000, can be 1 million. So it can be a large number. So if single current average is 10 micron, this is very conservative. If the average current during this period is 10 microns, 10 micron amperes, the peak current could be 100 micron, or even 200, 300. Depends on which kind of operation speed you want. So assuming 100 micron for a single current, peak. If n equal to 1 million, and this would continuously, then this current would be 100 milliamperes. And if you want to delta V in kind of fraction of 1 watt, you need tens of microns for the width, as you have done now. So this is very significant, not because switch more than, because dynamic operation. So this is a effective VDD for these units. And the problem is not that. The problem is this effective VDD could be VDD almost equal to VDD. If nothing, nobody is switching. It could be VDD minus 10% of VDD in a normal case. I'm not talking about worst case scenario, a normal case. So it is VDD like, this is regular VDD. This is, from time to time, you have such a thing. VDD like this is not constant echo. Big problems. And ground ones the same, because current flowing through will charge it, and next period will discharge. And that's I say you never reduce VDD, because the VDD is already ripple. And VS is also ripple. So your noise margin is even, without reduced VDD, noise margin is already reduced. So idea to reduce VDD to save power is not really a good idea. And operation, you have a lot of safety and reliability, and this is not there. So power dissipation or peak current is very important issue from operation point of view. On time now. Thank you. Good point. At least you know how to calculate in this case. How to calculate peak current.